by Changhe Yuan and James Cussens about optimal algorithms for learning Bayesian network structures.
Hello? Can you hear me well? Is it good? Can you hear me well? Yeah? Okay. Okay, so thank you for coming to our tutorial on optimal algorithms for learning Bayesian network structures. So I'm Changhe Yuan from CUNY Queen's College. I will present the first part on reproduction and heuristic search. And then James will present the second part on integer linear programming and the evaluation. So Brandon contributed to both parts of this tutorial, but unfortunately because of conflict in schedule, he won't make the tutorial, but he will be present for the latter part of the conference. So there's no need to introduce more detail about Bayesian networks. Suffice to say that a Bayesian network is a directed acyclic graphical model. So oftentimes we do not have Bayesian networks readily available. We have to build them, or we have to learn Bayesian networks from data. So for the learning approach, we want to learn both structure as well as parameters. So existing approaches can be roughly divided into 4 categories: score-based learning, constraint-based learning, hybrid approach that integrate constraint and the score-based learning, as well as Bayesian model averaging. So this tutorial will focus on the score-based learning. In particular, we focus on optimal algorithms for score-based learning. So briefly, score-based learning is to find a Bayesian network that optimizes a scoring function. So from this statement, there are 2 natural issues, right? One is how do you define a scoring function, and then how do you formulate and solve the optimization problem. So again, we focus on the algorithmic aspects of part, but because of the relevance of scoring function, I will touch upon it as well. So there are many scoring functions for Bayesian network learning. Here are some examples: Bayesian diversity, family scores, MDL, AIC, etc. So one thing that is important for our algorithms, especially our search algorithm, is the decomposability of the scoring functions if the data is complete. So decomposable means that the score of a Bayesian network structure is equal to the sum of the score of each individual variable given the parents. So, so we can explore this decomposability to devise efficient search techniques to solve it. During the learning, one operation that is repeatedly being used is the query, is this query. So the query is to ask what are the optimal parents for variable x out of a candidate set u. So if I give you variable x, I give you a candidate set u, can you tell me what are the optimal parents for x out of the set u? This has to be done repeatedly in the learning. To answer this query, you need to enumerate the subsets and find the best one. For example, if we want to find optimal parents for x1 out of candidates x2 and x4, so you need to enumerate the subsets of x2 and x4 and find the best one. So the naive approach just does that. So for example, if we want to answer query for x1, so this graph, we call it parent graph. This graph calculates all the raw scores of the parent sets of x1. So if the parent set is empty, what's the score? If the parent set is x2, x4, what's the score? And so on and so forth. So this gives you all the scores, and you can find the best one out of, for example, if you have a candidate set x2, x4, then the best one will be, the best parent will be x2. Okay, so here we are assuming minimization problem, but it's easy to convert between minimization and optimization problems. But if you do this, it's kind of inefficient. So an immediate improvement you can do is you can propagate the scores down the graph so that you have the optimal parents readily available. So this can be done from top-down fashion. For example, the optimal parent set out of x2 and x4 is x2, and that's already been propagated in that graph. Then, if you store this graph as a hash table, then you can look up the optimal parents in constant time. Okay, but still, this graph needs exponential space because there is an exponential number of subsets of possible parent sets for x1. So this theorem can
excuse me,
yeah,
what was the difference?
yes.
I missed what you meant by propagation.
So
what's the difference? Yes.
Right, so those are the raw scores.
Yeah.
So for example, this score is the score for candidate parent x2,
Okay.
x4. But when we are answering this query,
this is already the best score.
yeah, this is the best, that's the best score among all the subsets of this set.
Okay.
Right. So we don't want to store this exponential graph in memory. So this simple theorem, but effective theorem, can help us to do score pruning. So here, the basic idea is that if you have a subset and a superset, if the subset as parent set of x1, xi, has a better score than the superset, then the superset can never be optimal for xi. So that choice we don't have to consider it because it's never optimal. So we can achieve this pruning using two approaches. One is to compare the raw scores, compare the scores of PAI or PAI prime. But that requires us to calculate the scores. And oftentimes we don't want to do that. We want to prune some candidate parent sets without even computing them. So we can use properties of scoring functions without, such as exponential pruning technique, to prove that some supersets are worse than some subsets without even computing them. I'm not going into those specific techniques, but just take an example for MDR score, for the minimum description length score. We can prove that for a certain number of variables and a certain number of records in the dataset, the parent set can never have more than a certain number of variables in it. So anything larger, any parent set that is larger than the size can be pruned immediately. So that's an example of we prune the scores without even computing them. So after pruning, this is very important. Then each variable has a list of possibly optimal parent sets. We call them pops. So only those parent sets need to be considered. The scores of all those pops are called local scores. And the approaches we are talking about today typically assume those scores are already calculated, and we are just focusing on the optimization part. So for example, for the previous example, only half of the scores can be optimal, so only half of them are retained. And in practice, the number of pops is typically exponentially smaller than the possible number of parent sets. For example, here I list a set of data sets. The first number, so for example, adult data set has 14 variables and has 30,000 records. So you can see that the green bars show the number of local scores is exponentially. It doesn't grow exponentially as the number of variables. The number of pops typically depends on heavily depends on the number of records. Of course, the number of variables as well in a data set. So practically, even though we assume we have the local scores before we do optimization, but we still need to calculate them. So the most efficient way to do that is using sparse AD tree to collect the sufficient statistics, and then use a breadth-first scoring strategy to maximize the efficiency of exponential pruning. And Gaussian parallelization obviously will help in this regard. So the scoring part can be quite scalable. Of course, if we fail to do this step, then the optimization step is out of question. But this step can be quite scalable. Okay, any questions so far? Yes.
The sparse ADT.
Yeah.
What
So-
is it?
So it's
What
just
is
a
AD?
AD tree is a technique for you to collect the sufficient statistics on the different combinations of variables. How many counts of this configuration you have in the dataset? How many counts of that configuration you have this in the dataset, and so on. So the sparse is just help you to avoid have to enumerate everything because only some of the configurations are useful and are needed. Yeah. So the A and D, let me see. So one is the I forgot. So these are two kinds of nodes in the AD tree. So one is keep track of the configurations. The other one is I forgot exactly what A and D means, but that's what the purpose
It's a very
is.
clever way of coding data.
Yeah. To branch on the configurations, the values of the variables, and to get different configurations of so just to collect those counts. Okay, so now I'm ready to talk about our search formulation of the problem. So here we formulate the Bayesian network structure learning problem as a graph search problem. The shortest path solution to this graph search problem will be equivalent to the optimal Bayesian network. So this is the main idea. But let me use an example to tell you exactly what I mean. So this graph, don't know whether it helps or not. So this graph is an implicit search graph, search space for our algorithm. It contains all the subsets of the variables. So 1, 2, 3, 4, those are the variables, and each node is a search node in our algorithm. And so this graph is also a hash graph. So this is our search space. We have all the subsets of the variables, and then the top green node is the empty set. It's also the start node of our search algorithm. And then the bottom red node is the goal, is the complete set. It's also the goal node of our algorithm. So start node on the top, goal node at the bottom. And the arcs in this graph represents adding new variables to an existing variable set. Okay, so the different ways. So when we have 3, 4, there are 2 ways to add variables at 1 or at 2. There's a cost associated with each arc. For example, for the arc from 3, 4 to 2, 3, 4, it represents the cost of finding optimal parents for variable 2 out of candidate set 3 and 4. Okay? So this can be answered by using the parent graph, by the local scores, just to remind you. So once we have this search space and the formulation, then the task is to find the shortest path between start and goal nodes. So we start from the start node and try to find the best path or the shortest path between the start and goal nodes. Okay? For example, with this particular path, it corresponds to the variable ordering 1, 3, 4, 2. And so that's why we also call this graph order graph, because it represents different ordering of the variables. Now, because each arc encodes the choice of parents, if we put the parent choices together, then we have a valid Bayesian network and guaranteed to be optimal if the path is shortest. So that's the formulation. Now, of course, when we do search, we are not building this graph. We are not building this whole graph, right? Because this is the implicit graph. We want to search the graph by expanding as few nodes as possible. So so one technique we can use is the A-star search. So as you know, A-star search is a best first search technique that expands the nodes in the order of quality. So we typically use a function, F function, to measure the quality of such node. And the F value is equal to a sum of G value and H value. So G value represents the best cost so far from the start state, from the start node. And the H value is an estimated distance to the goal. So G is the exact cost so far, and H is an estimation. So G plus H give you an estimation of the total distance. And then A-star will always expand the one open node that has the shortest or the lowest score, lowest cost. So, so I will use red shaped outlined nodes to represent open nodes, which need to be processed or searched by A-star, and nodes with no outline as closed nodes. So we initially only have the start node, and we expand it, we calculate the G and H costs for the start node, and then we expand it because that's the only choice. So we generate the successors and calculate the G and H costs of all the successors, and all those nodes will be in the open list, and the start node will put on the closed list because it's already been expanded. So then we choose the best one and expand it, and so on. You can see that because this is a graph, so there may be multiple paths to the same node. For that, you need to do duplicate detection. That means when you do search, when you generate new nodes, you have to check whether the node has already been generated or not. And if yes, you need to update the G cost if the if a newly generated node has a better G-cost than the existing one. So this is standard A star operations. So we keep continue until we select the goal node for expansion. That's when we find a complete solution, an optimal solution, and we can stop. So then the path will be our solution.
Can I have a
Yeah.
question? What about where you come h? I think this h function estimated the way how this state must be the magic.
Yes, so I will talk about this. Yeah, I will talk about actually our different proposals of H throughout the tutorial. Yeah, so I will come to just that. H is the essence of A star, because you need to design H properly for A star to work, and you need to actually want this H to be as, so H is basically a lower bound for our search algorithms, and we want the lower bound to be as tight as possible. But firstly, let's just use this simple heuristic. So this heuristic function, HU, the basic idea, so it's a sum of best scores of X given some other candidates. So this particular H allows each remaining variable X, so V backslash U, those are the remaining variables. It allows each remaining variable to choose optimal parents from all the other variables. So this basically it relaxes the acyclic constraint for all the remaining variables. It's a relaxation. It also makes the computation of the H function very fast. But just as an example, suppose we are calculating the H value for node 1 and 3. The remaining variables are 2 and 4. So we allow 2 and 4 each to choose optimal parents from all the other variables, and that give us the heuristic estimation over the remaining variables. Okay? So this, even though this heuristic is quite simple, it actually satisfies two very nice properties. One is the admissibility property. So admissible means the heuristic estimate never overestimate the distance. It's quite important because this admissibility guarantees the optimality of A star once the goal node is selected for expansion. Okay. And actually, the simple heuristic also satisfies the consistency property. So the consistency, you can understand it as satisfying the triangular inequality, so which makes the heuristic estimates always monotonic, so it never decreases in any path of any search path. So the consistency is a stronger assumption or a stronger property than admissibility, because consistency implies admissibility. So consistency guarantees the optimality of the G-cost of any node once that node is being expanded. So if you remember, I said that there are different paths to the same node, right? Now, if a heuristic function is consistent, you do not actually have to check for duplicates, because once a node is selected for expansion, then the G-cost is guaranteed to be optimal. There's no way you can find a shorter path, another shorter path later on. So the consistency is a quite nice property. But if you just have the admissibility, you are fine, because that already guarantees the optimality of the A star algorithm. Okay? Any questions so far? Yes.
Can you take me through again how you get from the path to a network?
Okay. So So this path is represent the ordering of 1, 3, 4, 2, right? It's the order in which the variables are added. So 1, 3, 4, and 2. And then the arc, remember, it represents the choice of optimal parents from existing variables, right? So 1 can only select empty set, 1, 3 can select from 1, and so on. So when you put the parent choices together, there's no cycles. There's no cycles. So then you have a valid Bayesian network. And the shortest one give you the optimal Bayesian network. Okay? Other questions? Yes?
To compute the heuristic, if we assume the node can take any parents, don't we have an exponential number of subsets?
Yes, that's where when I was talking about the pops and the local scores, that's why we want to do pruning, right? Because we want to get rid of those useless scores in the parent sets. Only keep those ones that are potentially optimal.
So the pruning can make computing this
Yeah,
heuristic efficient?
Huge difference. It's exponentially smaller than the number of all the subsets. Yeah. Okay. Yeah. Another question.
But what you just said is it's an empirical result that on lots of examples you found that, but is there also some theory?
Right. So empirical because we only have finite number of records. We don't have infinite number. So because of that, in practice, the number of pops or potentially optimal parent sets is exponentially smaller than the all possible subsets. Yeah. If you have infinite amount of data, then you have to consider everything. You have to consider all subsets. All subsets are possible. But well, the exponential, so the exponential pruning actually helps that because when you have the theoretical properties of some the example I gave earlier, the MDL score, the minimum description length, with well, that's not a good idea because there's infinite number of records, but still for some scoring functions, it's typically a trade-off between, let's come back here, so the scoring functions are typically consist of likelihood plus a penalty term. Now if you can prove that the penalty term increases faster than the likelihood, then at a certain point the larger the parent sets can also be pruned. So I need to take the consider everything back because in some cases you can prove some supersets have worse scores than some subsets. Okay, so let me continue. So the A star, it needs to maintain an open list and also a closed list as well in some cases. So the space requirement in the worst case is exponential. So that's why we also applied another search strategy to solve the problem. It's based on this observation. So the search space, you can see that it has a very regular layered structure, right? And also, for a particular search node, the successors only appear in the very next layer. So because of those observations, we can do a layer by layer search. And during this layer by layer search, we can store, for example, the open list on disk. Okay? And we can actually when we generate new nodes, we need to do duplicate detection. But if we use disk, we can do delayed duplicate detection. So what we can do is we can write things first to disk, and then later on use disk sorting to detect duplicates. And we can also write those old layers. I graded, but here you can see. So I can write all the layers to disk to save RAM space. And that helps us scale up the learning. Of course, one thing we needed for the reference branching bound is an upper bound before the search. So we can prune anything with f cost worse than the upper bound. Okay, so here's a brief comparison between A star and reference branching bound. So James will compare different search strategies. So here I will focus on comparing different search methods. So you can see, so again, the x-axis shows the different data sets, and the red bar shows the A star, and the green bar shows the reference branching bound. So you can see the reference branching bound can solve larger data sets than the A star. So that's not surprising because it uses disk to store information. Okay. So I need to move a little more quickly. So, okay, now we have this simple heuristic, remember, and we immediately knew that the heuristic matters a lot for the search techniques. That's indeed the case. So for the simple heuristic, remember it allows each variable to choose optimal parents independently from all the other variables. So that completely relaxes the acyclic constraint for the Bayesian network. That will induce cycles. But for heuristic estimate, it's okay. It's only a guidance. We don't have to have acyclic solutions. But a potential idea is that if we get rid of some of those cycles, we can get a tighter bound, a tighter heuristic. So for example, if we consider the cycle between variables 1 and 2, there are two possible ways we can break the cycle. We can delete the arc from 1 to 2 and let 2 to rechoose optimal parents from the remaining variables, or we can delete the arc from 2 to 1 and let 1 to rechoose the parents. So among these two possibilities, if we take the minimum will still be admissible, will still guarantee to be a lower bound. So that's the idea. But in practice, we do not have to do cycle breaking explicitly. We only do it implicitly. So what we can do is we can generalize the cycle breaking idea to a technique called static k-cycle conflict heuristic. So the technique will divide the variables into static groups. So 1 to 6 we divide into 1 to 3, 4, 5, 6. So those are fixed groups. And then we calculate all the costs of the subsets of each static group. So for the group 1 to 3, we can calculate all the costs of the subsets by using a dynamic programming strategy. So we start from 1 to 3, we do backward search, okay? And each arc has the reverse G cost. For example, you go from 1 to 2, 1 to 3 to 1, 2 to 1, you can calculate the reverse G cost. And the cost turns out to be the heuristic estimate for variable set 1. So the heuristic estimate of this set with variable 1 is equal to the reverse G cost of 1. So by using a dynamic programming algorithm to do it bottom-up fashion, then we can calculate all the costs. And now those costs are stored in databases. So that's why we call this static pattern database as well. So once we have this pattern databases, we can calculate the heuristic of any node very easily. So for example, when we have the search node 156, what's the heuristic value of that? Well, what we can do is we divide the variables according to the static grouping. So we have h of 1 plus h of 5, 6. This can be looked up easily from the databases. So we can calculate the scores in constant time, still constant time. Okay, so this, so we call this static k-cycle conflict heuristic. The nice thing about it is it's a much tighter bound than a simple heuristic, and it remains to be admissible and consistent as well. So here, if we enhance, so the purple line is the A-star algorithm enhanced by the static pattern database heuristic, and it can solve larger data sets than the A-star with the simple heuristic. Okay, any questions for this part? Okay, so let me, question, yes.
When you said that the conflict heuristic is tighter than the previous heuristic, did you prove that it actually dominates it, or are you saying you?
Yeah, dominates, because you have this minimum. You break the cycles. So once you break the cycle, whatever way you delete the arc, you will incur a higher cost. So the admissibility. So we prove this, the admissibility and the consistency. So we prove the property in the paper. Okay. So now we have talked about the formulation of the shortest path solution approach. In the next part of my talk, I will present several different ideas. So the idea is that those formulation, the shortest path formulation is very general. It is not specific to any data set. But sometimes, if you can extract useful information from the data itself, that can often help improve the search efficiency a lot. So the first idea I will talk next is called learning decomposition. And firstly, the pops, remember they are potentially optimal parent sets. The pops turn out to capture all the possible parent-child relations between the variables. So here is an example. So I have all the pops for a problem with an example with 6 variables. We observe that not all variables can possibly be ancestors of others. For example, x1, x2 only have each other as parent, and x3, 4, 5, 6 can never be ancestors of x1 and x2. So what we can do is we can build the parent relation graph that aggregates all the parent-child relations in the POPs table, and then we create this component graph, which includes the strongly connected components of the parent relation graph. So for example, here we have the component graph, 2 components, one with variables 1 and 2, the other one with variables 3, 4, 5, 6. So you can see this gives you ancestral constraints, which tells you that 1, 2 have no other variable as ancestors. Okay? So this is very useful because the different SCC, strongly connected components, they represent independent learning problems. So what you can do is you can learn first the first component and then learn the second component. So so this is a new order graph. So the new order graph can be exponentially smaller than the old order graph. And because the top half and the bottom half, they are completely independent learning problems. So you can solve them independently. And even if one component maybe only has 1 or 2 variables, but in practice, that gives us a huge improvement over the search efficiency. And we can also apply this idea recursively, because once we enter a particular component, right, and once we expand a variable in that component, then we can delete some args that will give us sub-components to work with. So here is the example. Let's say we enter the second component, and the first variable is 3. And if we decide to expand 3 next, we will delete the arc between 6 and 3 because only 1 and 2 are considered as ancestors of 3. And then we have a sequence of single variable components to work with. That's only one possible path towards the goal. So, so if we apply this idea to this component graph, we realize that even though we have this exponential graph and also exponential number of paths, but only those red paths that is being marked are possible. So there's much fewer paths possible. Okay, so we apply this. So we call this POPs constraints and the recursive POPs constraints. So we apply this idea to our learning algorithm on several challenging data sets. So alarm has 37 variables. Initially, we can solve it within 80 seconds, but with the POPs constraint, we can solve it within 8 seconds. So one order 10 times faster. And recursive constraints helps a little bit in this case. So this is another data set, Barley, with 48 nodes. Without constraint, we couldn't solve it. Okay? But once we apply this POPs constraint and we are able to solve it actually pretty fast. It only took 2.5 seconds. So from not being able to solve it to 2.5 seconds, that's a dramatic improvement. And the recursive constraint helps as well in this case. And this is yet another data set, soybean, 36 variables. So again, we initially couldn't solve it, but with the POPs constraint, we can solve it within 430 seconds. Okay. But recursive constraint in this case didn't help, made things a little worse because it didn't help a lot, and there's an overhead of using this recursive constraint. Okay, any questions for this part? Okay, so let me continue. Now, there's yet another way to utilize the information captured in the data to improve such technique. And this is to improve the grouping used in the static K-cycle comfort heuristic. So remember, there's a static grouping used in the static heuristic, right? The grouping, the quality of the grouping turns out to be very important for the heuristic. The tightness of the bond can be dramatically different. So a good grouping intuitively should reduce the cycles between groups. So you have these static groups. So between the groups, there should be as few arcs as possible, as few directed cycles as possible, not only arcs, but directed cycles as possible. So a couple of existing methods we used for grouping has this common idea that we put more variables that are more correlated into the same group. Okay? So first we create an undirected graph using the different correlation measures, and then assign the edges weights to the undirected graph, and then partition the undirected graph into balanced subgraphs. So those are the existing grouping methods we used. We have two of them, parent grouping and family grouping. So these two methods are useful, but they are indirect method. There's a more direct method we can use based on the POPs, the potentially optimal parent sets. So here's another example. We have 8 variables here. These are all the POPs. Those POPs, again, they capture all the possible parent-child relations in the data set. Okay? So as a result, the directed cycles in any heuristic you are using, no matter what the heuristic is, the directed cycles originated from those POPs as well. So then the idea is that why don't we work with the parent-child relations captured by POPs and try to see what grouping is the best. So here, this graph captures all the possible parent-child relations in the POPs. Now, if we have to divide, say, into 2 groups, what would be the best one? The best one would be in the middle, right? Cut in the middle. So top half and the bottom half, because that gives us the minimum number of directed cycles between the 2 groups. So that's the idea, but how do we do it algorithmically? So this is what we proposed. We try different number of top K POPs. If we only use the top 1 POPs for all the variables, we get this component graph. I don't know whether you probably can't see the component, but there are 4 components for this graph, and we can try to group them into 2 groups if we only need 2 groups. But we can try k equal to 2, and it turns out that when we have k equal to 2, we only have 2 components, 1 top component and one bottom component. So that gives us 2 groups, and that's turns out to be the best we can do. So we try k equal 1, 2, and so on until we get the largest k that will give us the 2 groupings. And so this pseudocode captures this idea. We will set a limit on the largest pattern database because if we don't have that limit, then it could be possible that the largest pattern database has all the variables or most of the variables in it, and that's almost equivalent to solving the original learning problem. So we don't want to do that. When we create a heuristic, we only want to do it fast. So we set a limit on the largest pattern database and then try different Ks and get the best grouping possible. We call it component grouping. So we apply this component grouping to the solving data set by varying the K. You can see that when we increase K from 1 to 2, the speed improvement is orders of magnitude. And when we increase to 3, there's a further improvement. But 4 and 5 didn't bring further improvement because the grouping turns out to remain the same. So here are results on 3 data sets: barley, soybean, and flag. So here we are comparing two existing grouping methods. This blue one is the new method. So you can see we achieved orders of magnitude improvement on these several data sets. Now, I have to say that the latter 2 techniques, they may not help for some data sets. They only help for certain data sets if those data sets have those phenomena that we observed. Okay, to summarize my part of the tutorial, we proposed this shortest path formulation of the Bayesian network learning problem, and we can apply standard techniques such as A* and reference branching bound to solve the problem. For this formulation, the design of upper and the lower bounds is very critical for the performance of this algorithm. And another point I want to make is the actual information extracted from data oftentimes help your algorithms. So your algorithms should be a general approach. But then, oftentimes, information extracted from data can help your algorithms to achieve better performance. So if you have to take only one message with you, I think methodology and data work better as a team. So the algorithms we implemented is available in open source software available from this website, urlearning.org. So you can download all the algorithms as well as the datasets we tested from this website. So I will here I acknowledge the support of several grants, and here's a list for left references for the techniques for the algorithms. Okay, thank you. So I probably have limited time for answering questions, but I can take maybe one or two. Yes.
One question, you were doing forward search where you start with the empty set, you go for a complete set. Sometimes it can work better to do backwards. Would that just be dual, like just change dual and start state, or?
Yeah, it's doable. It's doable. But when we tested, it didn't work as well as the forward from empty to the backward. But yeah, but it's completely doable. Yes. So, but we can discuss more details if you want. Yes.
As far as I can see, you get the optimal network out. Do you also get something like the second best, third best, etc.? Would that be?
We didn't do that in our approach, but that's possible. Yeah, you can say continuous search, but then you have to change the search space a little bit. So that there is actually new work by UCLA in this this GKR workshop. They did that extension. Okay, thank you.
Okay, so welcome to the second part of this morning's tutorial on exact algorithms for learning Bayesian networks. I'm going to be focusing on two topics, the use of integer programming to solve this problem, and a separate thing, empirical evaluations, which answers the question you're all waiting for, does this stuff actually work? Okay, so we'll start with the integer programming stuff. So the key to understanding this approach is to think of directed graphs. These are things we're trying to learn. Think of them as points in space, in Euclidean space. And this is how we encode them. So if you look at that digraph there, the digraph directed graph, with three variables, I, J, and K, you need to think of this as a point in 12-dimensional real space. All right? So don't think of it as a graph, think of it as a point. What is that point? We encode it using these POPs, basically, or we call them family variables, which Changhe has already introduced to you. So with I, J, and K, so for variable I, there are four possible parent sets, the empty parent set, J on its own, K on its own, and both J and K. So to encode that graph there, we have these, a vector with 12 components, and that one there has a 1 for the parent sets which actually obtain in that graph. And I hope you can see that any graph with those three variables can be encoded as a 12-dimensional vector with just ones and zeros in it. Okay, so that is that's the most important thing to understand about this approach. So we flip between thinking of these things as graphs and thinking of them as points in space, and that's one of the kind of nice things about this approach, because we can think about the problem geometrically. So in this particular case, you see that we have the guys in red there are the ones that are set to 1, and all the rest are set to 0. Obviously, we have the way I've written that 12-dimensional vector, I've written it in these 3 rows. There's always going to be exactly 1, 1 in each one of those rows. More on that later. People happy with that? Feel free to stop me at any time.
So I'm sorry, it's just going to be a vertex in that space. You
Right.
talked about Euclidean space, but since it's all 0, 1, we're going to find ourselves at some vertex.
Yes, this will. I haven't got to the.
Fine.
I haven't bounded this space yet.
Okay.
That will come. All right. So yeah. So before we get to bounding the space, let's talk about the objective that we're trying to maximise. So just there's possible confusion here. Changhe always describes his algorithms in terms of minimising something. I'm going to think of it in terms of maximising it, because we're trying to find the network with the highest marginal likelihood. So we're maximising now, folks. Okay, so what is the thing that we're maximising? Well, imagine we've got a graph, G. We've encoded it with this encoding that I had in the previous slide with these things we call family variables. So xg is this possibly very, very long 0, 1 vector. And we assume we have a decomposable score GD there, so we've got some data D. It follows that we can get that score by just looking up which parents each variable has in the graph. There will be some number, some local score. We just add all those guys up. And then we can also think of it in terms of this component xg. So that xg at the end there, most of the components will be zeros, so they won't contribute to the final score. The cases where we have the appropriate parent set for each vertex will have the value 1, so theCij's there will get added up. So that's why we have that final equation there. So what we have here is an objective which is a linear function of these family variables. Right, it's a linear function, that's the key thing. So that's why we can use integer linear programming. So the vanilla, so assume we don't have any extra constraints, which more later, the kind of standard approach, standard thing. The optimization problem is that we've got to find a particular, or maybe there'll be several, but one will do, an x hat, as we want to call it, such that it maximizes that linear objective, and of course such that the vector in question represents a graph, an acyclic graph. Okay, that's quote all we have to do. All right, so it's a very simple problem presented as such. So of course the key thing is what are the constraints we need to add to make sure that 2 is the case. So let's start talking about that. Here are those constraints. So there aren't too many of them. Well, sorry, there aren't too many classes of them. There are exponentially many of them. So the first one we have is that one which we call convexity, is to say that for any particular vertex in the optimal graph, which we will eventually learn, that vertex has exactly one parent set. Yeah, there's only one parent set. It might be empty. So therefore, if for each I we sum over all those components representing different choices of parent sets, different pops, that adds up to 1. Right? So that is a linear equation. That, if we have that on its own, with the integrality thing, then we'll always get a graph at least get a graph. But we want acyclic graphs. So then we have to rule out cycles. There are many ways of doing this. There are kind of simple, obvious ways and more complicated ways. The way I'm going to present to you today is these things called cluster inequalities, introduced first of all by Yuan et al. Quite some time ago. So how do these cluster inequalities work? We say for any subset of the vertices, so C is a subset of the vertices, it must be the case that one element in that subset has no parents in the subset. That's what that is saying. So it's easier explained with an actual Bayesian network. So if we have a look at this Bayesian network, which some of you may be familiar with, if we take C as the whole set, then we have 2 variables, A and S, with no parents in that set. Yeah? If we, for example, have, I don't know, give me a subset of them, S, B, and X, then we have 2 variables which have no parents in that set, namely X and S, because X is the variable E, which was not in the subset in question. Any subset you give me, there will always be a vertex who has no parents in that subset, if it's acyclic. Yeah, if it's cyclic, that will not be the case. Okay. So if we were to put every single such constraint into our integer programming problem instance, then we can be sure we wouldn't get a cyclic graph. All of a sudden, if there's ever a cycle, one of these guys will be violated. So that, again, linear constraint. Exponentially many of them, which we'll later. And the last constraint is that our vector, our real valued vector, in an optimal solution, we only want zeros and ones there. Okay? So it's got to be an integer vector. That then gives us an integer program. It's an integer program because the objective is linear, and the only constraints are linear as well, plus the constraint that some, in our case all, of the variables are integer. So that's what an integer program is. Feel free to stop me if I'm flipping past them too quickly. Okay, so at this point, you're thinking, why has it got such a complicated way of ruling out cycles? There is good reasons for that. But first of all, let's talk about relaxation. So solving relaxed versions of problems is absolutely key to any integer programming approach, and certainly the case for Bayesian network learning. We start off, so the system that I and colleagues have developed called Gobbledygook, it starts off with a very relaxed version of the problem. We remove first of all, we remove the constraints, well, we don't have, as it were, we have 0 of these cluster constraints, all right? So cycles are allowed to begin with. And also we drop, so that's called a combinatorial relaxation, and we also drop initially the constraint that x has to be integer valued. Okay, so x. So these family variables, which eventually will have to be either 0 or 1, now they can be 0 or 1 or any number in between 0 and 1, like a third or 3/4 or whatever. But we just have that constraint at the top there. Okay? So we can solve that problem very easily. It's a very easy problem to solve. Why do we do that? Why do we solve relaxations in general? We solve them because they give us an upper bound on the eventual optimal solution, because we've thrown away some constraints, so evidently we're going to get an upper bound, because we make life easier for ourselves. Also, eventually we might get lucky. If we solve the relaxed version of a problem, and lo and behold, it happens to meet all the constraints that we've thrown away, then we're done. Okay, so that's how we prove optimality, by solving a relaxed version, which is generally more easy to solve, and we get lucky. So suppose you can have very artificial examples where just with those constraints up the top there, you might get an acyclic graph, and then you're done. Typically you wouldn't. So that's what relaxations are there for. Obviously this is a useless relaxation, right? This will not solve the problem for us, so we need to do some work to improve it. So the way we do so is by adding adding some of these cluster constraints in, the ones that rule out the cycles, all right? But we don't add them all in, mainly because there are exponentially many of them, so that's impossible, and also we don't need to add them all in. So how does this work? So first of all, what we do is we solve the relaxed version of the problem. Okay, so initially it's just this guy. Sorry, initially it's just this guy with those small number of constraints. So we solve that. We get a solution, which we're going to call x star. Then what we do is we say, right, well, we've got these cluster constraints. We'll need a pointer. So we've got these cluster constraints which say that blah, blah, blah has to be at least 1. If we can find a subset of variables C, such that is not the case for our particular solution, x star, then we know that we found a constraint which needs to be there, which our current solution violates. Okay, so that's what we're looking for. We're looking, so for example, yeah, so then what we do is we add that constraint to our problem. We get a new relaxed problem with an extra constraint that we didn't have before. We then solve that guy. Okay? And then we keep going over and over again, adding more and more of these constraints. At this point, the integrality constraint, the constraint that eventually all these variables have to be either 0 or 1, we don't put that in. So we're continually solving linear relaxations, but linear relaxations with more and more constraints in it. Each time we add one of these constraints, our upper bound will go down, because previously we found the solution which we found this solution here, think of it as a point in space. Then we found a linear constraint, which we think of as a hyperplane, and this guy was on the wrong side, as it were. So if we add this constraint, then we can't get to this guy anymore. We're going to end up down here. All right, so we're constantly, think of it as chopping away, yeah, and then chopping downwards. Also, we might get lucky. It might be the case that if we add enough of these constraints, we solve our linear relaxation, and even though we didn't require the solution to be integer. It turns out it is integer. Happy days. We also use, the system I use uses a system called skip, which also adds in some extra cutting plane algorithms as well, things like Komori cuts and so on, which I haven't got time to go into. So all sorts of extra constraints being added. Okay, so this is known as the cut in ILP, so adding constraint after constraint. So the big question here is, how do we find these C's? Yeah? So there are exponentially many of them because there's one for every subset of our vertices. So, so there's this problem of finding a cutting plane. So it's called a cutting plane, by the way, I should say, because it cuts off the solution that you've just generated. This problem is known as a separation problem. It's known as a separation problem because you've just generated a point here and you're trying to separate that out from the set of feasible solutions down here. It's a separation problem. So there it is. Find a C such that the variable is such that our current solution violates the relevant constraint or show that no such C exists. The bad news is that that problem has recently been shown to be NP hard in a paper which will eventually be made public when my co-authors get less fussy about it. Anyway, we have shown it, well, my colleagues in Helsinki have shown that it's an NP hard problem. In the system that we've developed, how do we solve this NP hard problem? We have another integer program inside the main integer program. We have a sub-IP. So each time we solve that, we have a sub-IP which we create. We use it to find a C. We try and find a C which violates such that the X star violates the constraint as much as possible. All right, we want to make a deep cut. So that's kind of how it works. Most of potential equalities for different values of capital C that are not added because they're not needed. They're not needed to improve the bound. So at the moment, all we're doing is improving the bound. We may not have found any Bayesian network solution whatsoever, let alone not to the point. We're just improving the bound. Okay, so that's sort of how it works. So here's an example of this in action. Okay, so this is a steady extreme example. So we're dealing here with a case where we've got 1,614 variables in our Bayesian network, which sounds like a lot. However, this Bayesian network represents a pedigree, which is a family tree. Could be a graph actually, but what people normally call family trees. So there's at most 2 parents for each node, which means that when you convert it into these into our representation, we don't have that many variables for the integer program because we've restricted them to parents to 2 because you only have 2 parents. Yeah? So that's fine. So we only end up with 11,000 or almost 12,000 variables in our integer program, which is not that much for an integer program. Anyway, and this is an old version. We've got it's now much faster, of course. So this is us generating these guys. So next, so at the beginning, you see that I've cut off the start of it. We've added 661 of these cutting planes. We solve the linear relaxation, and we find 120 of our variables are fractional. Okay, so obviously we don't have a solution because of. And then we add another 8, and solve it again, and we end up with 118 fractional variables. Then we get a few more cutting planes, blah blah blah. Then we get down to this situation here. We've got 103 fractional variables, and at that point we've added 685 of these cluster constraints, and maybe some other things as well. We then spend a good 40 seconds looking for some more cutting planes to add. We add the grand total of 7 to get us up to 692, and we have a new linear program. We solve that linear program, and we get lucky. Hooray! Turns out that the solution for that linear program has no integer variables whatsoever. And then we do a final check, so therefore it's a graph. Then we do a final check that it's an acyclic graph, indeed it is, and we're done. Okay, so at this point here, this star, this skip notation saying, the solution to your linear program meets all the integrality constraints, you have a new solution. So here we have the bound, this is the upper bound, which as you can see is going down, down, down. The primal bound, this is just the value of the best network bound so far, so we found some crappy network early on. Yeah. Really miles away from the optimal, and then once we solve this linearization, we're done because the upper bound and the lower bound are both met, problem solved. Okay, typically this doesn't happen. Typically you have to do branch and bound, of which more later. Move on. There'll be more on this example later on. So pretty much that's what's happening every time we use this IRP approach. So now I want to just give you a bit more insight into the cutting plane approach, and it's much easier to do that with 2 variables rather than 11,000 variables, because I'm not very good at visualizing such high-dimensional spaces. So imagine we just had 2 variables. And imagine we have an objective, so the objective there is represented by this blue thing, so the further up the blue arrow you go, the better your solution is. Both our x and y variables, we've said they have to be integer, so only where the black dots are, they are feasible solutions. Well, not all of them are feasible solutions. And we have, unfortunately the green hasn't turned up very well, we have 1, 2, 3, 4, 5, 6 linear constraints which are mapping out this feasible region. Okay. So how does an ILP system solve such a problem? It would first of all solve the linear relaxation, which would take us to that point at the top of our irregular hexagon. All right, so that's what we would do.
There's a laser pointer on the table.
Oh, there is? Ah, things will go better now. Right, so you will solve the linear program, and you'll end up here. All right. So what happens next? We know, because this is easy, we know that's the optimal solution. All right, but the algorithm won't have worked that out by now. So a cutting plane basically says is where you add a constraint which chops off part of the feasible region, but doesn't chop off. You know it doesn't chop off the optimal solution. So we'd end up with a smaller feasible region, a smaller polygon. Just think all the time in terms of polyhedron in high-dimensional space. So if we solved our linear program next time, we'd end up here. Right, and this would be a lower bound. We get a better bound on the conventional solution, which makes us happy. So that's what a cutting plane looks like. Okay. Obviously, it would be better if we added this constraint and this constraint. If we somehow added these guys, then next time around when we solve the linear program, we'd end up here, and we solve the problem. Okay. So this means that the key thing in ILP approaches is when you're adding these, if you're taking cutting plane approach, which most people do to some extent or other, you want to add cutting planes which are, as it's just you introduce some terminology, you want to add cutting planes which are facets of the convex hull. That's what you want to add. So you'll see here, these dots here, we could create the convex hull of this, which would have 1, 2, 3, 4 sides to it. This guy and this guy, they are facets of the convex hull, which means they define the convex hull. And you'll notice that we've added just 2 of these facets in. We didn't need to worry about the ones down here, because they're far away from the optimal solution. Adding these guys in was enough. Okay, so what we're always trying to do is add tight inequalities in as much as possible. So that's kind of where you're hoping to go with an ILP approach. Of course, it may be, maybe we can't find any cutting planes, or maybe the cutting planes we find just snip off a tiny little fraction of our feasible region and not really helping as much. What do we do then? Then we move to branch and bound. Okay, so in this situation, what we might do is to say, right, we can't find any more cutting planes, but we know that our x variable here, the x variable here has to be integer. Therefore, we know either it's at most 2 or 3 or more. All right? So then we chop the problem into 2 sub-problems, and a nice chunk of the feasible region with non-integer solution disappears, which is good. And then we just work on this guy and this guy. Yeah? Again, looking for cutting planes and so on either side. And we can do some interesting things here. So suppose that we started working on this side of the problem first. All right, so we ended up here. And suppose we found this cutting plane here to just chop this bit off. You'll notice that it hasn't got us to having an integer solution on the vertex, but never mind, we've made some progress. Suppose also that by some heuristic algorithm, we'd found that this guy here was at least a solution. Maybe we hadn't proved it was an optimal solution, we found this guy. This was our incumbent, as it's known. Now let's just think what's going on here. We look over here, we've solved the linear relaxation, we've got to this point here. This has a worse score than some existing solution. It therefore follows that this side we can just prune away. Okay? So this is what lies behind branch and cut. So once you've done some branching, you also try and add cutting planes to your new sub-problems, and you also solve the linear relaxation for each node in your search tree in the hope that you can do this sort of thing. Yeah? And what this shows also is finding a high quality incumbent solution early on really helps you. Because the sooner you find, suppose we found this guy, and we ended up, this guy down here, we couldn't do that, could we? Because maybe there'd be another thing over here. Now we can. So I don't have time to talk about finding the incumbents quickly, but that is actually an important part of the whole process. Anyway, this is the branch and cut approach. So you branch and you cut, and that's how it works. So, this is the branch and cut algorithm, which lies behind the approach of Bayesian learning. So for any node in your search tree, including the root node, you solve your linear relaxation. If that's worse than the incumbent solution, if you have an E, then you're done, as demonstrated just previously. Otherwise, if you can find some valid linear inequalities which are not satisfied by your linear relaxation, and you add them, you go back to 1. Just constantly adding things. If the solution to your linear relaxation has all the integer values it's supposed to have, then you're done. Happy days. Otherwise, you have to give up and find some variable to branch on to create two subproblems and keep going. And there's also propagation possible, but more of that later. So that is the branch and cut algorithm. That is the basic algorithm that's being run with this golden milk system, which I will be releasing more to you later on. Okay. So a little bit of theory here. So I mentioned things called facets and convex hull. Just to give you a bit more insight into this. So evidently, for any Bayesian network learning problem, theoretically you can code each solution as a point in a suitably high-dimensional space. Then you've got all these points in high-dimensional space. There is a convex hull of all these points. It exists. If you threw in all the inequalities defining this convex hull, then you could just solve a linear program, and you'd be guaranteed that the solution to that linear program would be an integer solution. Okay, because it's the convex hull of integer solutions. Every vertex is an integer, because the solution to a linear program is always the vertex of whatever polytope you defined will be done. Of course, the problem with this is that the number of inequalities defining any reasonable convex hull for any reasonable problem is astronomical, so you're not going to do that. Okay? Which is unfortunate because an LP, linear program, unlike an IP, can be solved in polynomial time using the ellipsoid algorithm. Typically we use the simplex algorithm, which is actually worst case exponential, but who cares, maybe worst case it never happens. In reality, we send it to Cplex, and let Cplex decide what to do. Anyway, so just to give you an idea of the size of these things, if you just have 4 Bayesian network variables, no doubt all of you know this number by heart, there are 543 acyclic digraphs. Okay? If you do this mapping, you can actually, because it's quite small, you can compute the convex hull. I think Matty probably maybe here. Yes, he did it using Polymake or something. You have 135 inequalities. As soon as you get bigger than 4 or 5, the number of inequalities is just colossal. Okay, that gives you some idea there. So, these cluster inequalities, why are they the ones to add? And we have to go to this trouble to solve an NP-hard problem to find them. It's just, there are easier ways of ruling out cycle, I can assure you that. Why go for these guys? Because these cluster inequalities, each one of them is a facet of this convex hull. Each such inequality is one of the tightest possible inequalities for our problem there is. That's why they're good to add, because if you add those guys, you'll be reducing your upper bound more quickly than if you added some loose inequalities. So it's worth the effort to finding these inequalities. Okay. So various papers, some in archive, some that seem to be in archive, have different proofs that this is indeed the case. So they were first introduced, as I mentioned, by Yapala, Sontag, Robertson, and Ryder. So they introduced and used a different ILP approach, which unfortunately I don't have time to go into. So they are facets of the convex hull. They are not the only facets. There are other things which are facets of the convex hull. So for example, with 4 nodes, it so happens that this inequality here is a facet of the convex hull. It's saying if you add all these guys up, they can reach at most 2. So the kind of way to think about it is, if A has B, C, and D as a parent, all these guys have to be ruled out. So that's where you get most 2. But you could have A having B and C as a parent, and there's a D having A and B as a parent. That's all right. But if you have that one set to 1 and that one set to 1, all these other guys have to be 0. You know. Anyway, so that would be a good one to add as well. You just have 4 variables anyway. So finding facets of these various convex hulls is a useful thing to do, because then you can go and search them and add them to a linear program and get nice tight bounds. So the theory is worth the effort, basically. Just want to, how we do? Okay. Digress briefly onto an alternative way of doing things. One of the problems with this encoding of digraphs is that really when we're doing Bayesian network learning, what we care about is not so much a particular graph, but the Markov equivalence class of which that graph is a member. So it's a bit, you think, well, this is a bit stupid, but we're going to have maybe many solutions corresponding to basically the same conditional independent structure. Can't we do better? And indeed we can, in a sense. If we encode our problem using these things introduced by Malone, called characteristic insets, then we have encoding where we have a 0,1 vector for each Markov equivalence class, not a 0,1 vector for each digraph, as I've shown you before. How do these 0,1 vectors look like? For each set of nodes S, your 0,1 vector, your characteristic inset for that S, you can actually define it in terms of the variables that I've shown you previously. So it's maybe easier to do by example. This Bayesian network here, the characteristic inset corresponding to the set T, L, and E, that has value 1, because E has both T and L as parents. The inset corresponding to the set AT, that has value 1, because A is the parent of T. But for example, I don't know, the inset corresponding to S and X has value 0, because S is not the parent of X and X is not the parent of. So you can do this correspondence between the two, which is quite useful. Also, at this very conference, we have yet more abstract approach using matroid theory to show all sorts of useful results about the inset representation and also this family variable representation and the polytops, the two things defined. Very nice paper. I encourage you to do it. That includes a nice proof that these clustering inequalities of facets are much simpler proof than the other ones, and also some other things in facets using matroid theories. It's all good stuff. Okay, enough theory. Let's move on to finish the ILP stuff. So I mentioned a lot about cutting planes. What if you can't find a cutting plane, or that you decide it's taking you too long to find cutting planes? You need to find a variable to branch on, and start the search tree. How do we choose which one to go for? So the goal in ILP is usually to choose a variable such that when you branch on it and generate two subproblems, the solution to the linear relaxations of these two subproblems, both of them, is much better than when you started out with. So you're trying to reduce the bound all the time. Eventually you hope to get a solution as well when they get bound on it. So the skip system uses something called strong branching. So it basically says, I want to choose a variable which will give me a good bound from the linear relaxation. How do I know which variable it is? I don't, so I'm going to try them all out. So I'm going to try variable number 1. Originally split the problem into two, solve two linear relaxations, see what they look like. Move on to the next variable, try that. And do a lot of work to try and choose the best variable, and experimentally if you like. So that's known as strong branching. This tends to give you very good progress in reducing your bounds, your upper bound. However, it's expensive because you have to solve lots of linear programs. So typically at the top of the search tree, you do a lot of this sort of stuff so that the variables you choose at the top of the search tree are good ones, and later on you're a bit more heuristic about it. Yeah. So that is actually, we take this default approach in the ILP system, because we haven't found a better one. And you can also do things like propagation. So obviously, if you've branched on these two variables, and you're in the branch where this guy's set to 1 and this guy's set to 1, then evidently you can't have this variable set to 1 because you get a cycle, so you just immediately set it to 0 using normal constraint propagation approaches. So you don't have to wait to solve linear relaxation. So we do propagation as well as always cutting plane malarkey. So in a recent paper, Van Beek and Hoffman have approached this problem and used a very much constraint-based approach to doing it with lots of propagation and no cutting planes at all. So propagation is also an important thing to have in your system. Okay, so we've made this system called Gobnilp. How does it work? Pretty much it uses the techniques that I've just been explaining to you. Basically, when do we stop looking for cutting planes and start branching? If after 10 rounds of looking for cutting planes, our bound does not improve much, we give up and start branching. Setting this number from like 10 to some other number will give you radically different performance. So it's, as you might expect. We also create some auxiliary variables, so we have these family variables, but then we also create variables representing edges, both directed and undirected in the graph. They're just linear functions of the original variables, so they're easy to create. we actually branch on those variables, not the actual family variables, because that gives us a more balanced search tree. That's just a detail. And we use Skip's default branching rule, which is called this, which is reliability pseudo cross branching with strong branching. Okay, so, but we use some non-default parameters just to, because it works better. So I don't want to go into that. So that's kind of how we do it. So it's probably worth mentioning that one of the nice things about the ILP approach is that you can throw in other constraints without coming up with a new algorithm. So if you have additional constraints, you just add them and just carry on as the normal state. Easy constraints like certain arrows have to be there, certain arrows can't be there, certain immoralities have to be there, that's all very, very easy to do, so I won't go into that. Maybe more interesting is conditional dependence constraints. So suppose you, the user, happen to know or wish to impose a conditional dependence constraint on the eventual Bayesian network that will be learned. Okay? So it's interesting, if you look at these cluster constraints, they say this thing, yep? They say that any expression like this has to be at least 1. Let's consider the case where for some C, this linear expression equals 1 exactly, which means it meets this constraint. So suppose it equals 1. What does that actually mean? What it means is that the vertices in our big C here have a single common ancestor. So for example, in this case here, suppose our C dash was, I don't know, SL and B. Yeah? You'll see that the value, there's only one guy which doesn't have parents in the set. L and B both have parent, namely S in the set, so it's 1. So there's no cycle, but it's only just met the constraint. Whereas if you take the whole cluster here, we have 2, A and S. So the value would be 2. But if it's 1, what it means is that all the nodes in C dash have a common ancestor. Therefore, that means they are deconnected. Therefore, that means that if you want, for example, J and K to be independent, suppose you're adding that as a user constraint, then it must be the case that for any C containing J and K, this constraint, you can tighten it from being at most 1 to, sorry, at least 1 to at least 2. Yeah? So you can think of these conditional dependence constraints as a kind of tighter version of these simplicity constraints. So if you, so we've implemented that, so if you add in some conditional dependence constraints, then we have a constraint handler which looks for these guys as cutting planes. Okay, and it recycles some of the stuff from the acyclicity cutting plane stuff. So that's kind of interesting, I think. And also you can add in other constraints. So you can say, right, I want a graph with no immoralities, no V structures, because I want it to be equivalent to a decomposable heuristic graph. These are easy to put in, and they're there in Godmilk. I have to say that the performance is substantially worse than an alternative approach by Cussens and colleagues from Helsinki, so they have a better way of doing it, but we do can at least do it. And I've done some work with people at Warwick, where rather than learning a single Bayesian network from a single data set, you learn multiple Bayesian networks from multiple data sets, and you have penalties for these Bayesian networks different from each other. It's kind of quite easy to do it. You just add in auxiliary variables, put in a cost for them being different, blah, 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 and then you can do this on hierarchical stuff, which is quite cool. So basically, you can add to it fairly easily. Okay, so what's the big problem with all these optimal approaches that we've shown so far? The big problem is that, well, for Godmilk and other ones' approaches, is that what we do at the moment is we generate all our IP variables before solving, and then try and solve for these variables. Evidently, if there are too many such variables, then we're going to run out of memory, something bad's going to happen, all right? So which is not very impressive, or it will get very slow. By the way, it's not the case that limiting the parent set size is the way to fast solving. You can always re-encode any Bayesian network problem where you need any Bayesian network problem where each variable has at most 2 parents or just creating extra fake variables. Yeah, but doing that doesn't really help you because you end up with just as many, actually slightly more integer programming variables. So how do we get over this problem? Well, at the moment, I don't think we really have done, but one potential approach is this technique from integer programming called column generation. So column generation is just another word for variable generation. It's called column generation because when you're solving a linear program, you need to think of your constraints as representing rows in some matrix, and your variables as representing a column. So you generate a variable. That linear program matrix has an extra column in it. So how does this work? Basically, we create new variables during the course of solving. So far we just create constraints in the course of solving, which has helped us. I think it would be useful to explore creating variables in the course of solving. So rather than generating the variables ahead of time and then just sticking with a finite set, you look for new variables as you go along, in the hope that you can do that more efficiently and scale up a bit more. So you add new variables. You add a variable if it can raise the upper bound. So then you move to a situation where you're adding cutting planes to reduce your upper bound, and then you're adding new variables to increase it. Yeah? So you're kind of going in two different directions. So adding new variables is known as pricing, adding new constraints is known as cutting, and so the algorithm you end up with is known as branch price and cut. So this might be a way, I'm saying it is because we've actually done this, but this might be a way of scaling up these approaches to having more variables available. But that's just a speculation at this point. Okay, so I think we're supposed to end at 10:20. I just want to talk a little bit about empirical evaluations of various of these algorithms. So maybe this would be a good point for questions. Are there any?
Can you re-explain this with the new variables? What did you mean by this? Where did the new variables come from?
Okay, a bit more. Okay, so the way to think of it is as follows. The way to think of it is, what you would do is you would start with a certain number of variables, normal variables into your program. Then implicitly you have in your mind a vast pool of additional variables. Okay, and the way to think of it is that these additional variables, which are not yet there in your system, they are clamped to the value 0. Right? You've got an extra constraint which is saying all these other variables, which I might eventually add, they're kind of there conceptually, but they have the value 0. Okay? I've got a constraint.
So the variables, are there other parent sets? Or
yes, there will be other parent sets.
Oh.
Yeah, sorry. That's an easier explanation. Not bad.
How do you deal with numerical accuracy issues? Like, can you recognize a solution if it's within the epsilon of the service?
That's a good question. Yeah, so as with all ILP, so when you, there are all sorts of numerical issues, which we basically assume Skip is dealing with, so we don't deal with that. But it is true that, you know, sometimes you'll get you're solving linear relaxation and some 0,1 variable will have value 0.9999999, and you're thinking, is that some rounding error? Is it really 1, or is it actually 0.9999? So that is an issue. I personally don't deal with it in my algorithm because I assume that the Skip guys in Berlin have done as good a job as possible. But you're right, it is an issue. Also, by the way, in the scoring, these local scores, if you have a very, so we're using BEE scoring, you may know, if you have a very, very large equivalent sample size, you can get numerical inaccuracies. You've got to be careful there. I'll continue. So, you want your copy, continue this. Right, empirical evaluations. So just a little bit about our own system. So as I said, well, I didn't say this. We've been funded to work on these pedigree learning problems where you have, at most, where your Bayesian network represents a graph of relationships between individuals and their parents. This is very tailor-made for the IP approach because you only have at most 2 possible parents. That makes life a bit easier. So that means we push the boat in terms of the size of the network because we can get away with that. So you have at most 2 parents, a known father and a known mother. So you don't end up with that many variables when you encode it as an integer program. So not too bad, only like a few tens of thousands maybe. So here's an example we've been working on. So the experiments we did, we took this pedigree, which is apparently a real pedigree, some real people were related in this way, so I'm told. And we simulated data from it, genotypes, like we put genotypes in at the bounds at the top there and dropped them down. And then so we get some data, and then we give the data to our system and saw how well it did at reconstructing the pedigree from which the data was generated. So that's what it looks like. Inuits have interesting habits, which makes the pedigrees interesting. Marriage chains and things. Anyway, so that's what we did. So how does it work? So we compared our approach to a heuristic approach called Franz. As you would expect, because our approach is always giving you a guaranteed optimal solution, the one with the absolute maximum likelihood, it takes longer. It's not massively longer. So this is Franz. Franz always takes about 10 minutes to solve, whereas Golden Milk often takes around 10 minutes, but occasionally you get unlucky, it takes 40 minutes. Yes, it's a bit more all over the place. There's a few cases. So this is just a normal box thing, so that the bar here is the median, sorry. These are the interquartile range in the bigger box. So solving times are kind of comparable. Our system is slower, unsurprisingly. Is it worth, so this is the key thing, is it worth trying one of these optimal algorithms? So you're busting a gut saying, oh, I've got to find the optimal network, I've got to find the optimal network with the highest score. At the end of the day, you don't care about the score, you care about identifying the true network or something, you know. Does this actually help you? Well, certainly in this case it did help you, not massively. So when we reconstructed the networks, we get slightly higher precision of recall. So both do pretty well, but we get slightly higher. So I think it's, when we talk to our colleagues who work on pedigrees, we have ecologist problems, and we say, oh, our system takes half an hour to solve this problem, we're very embarrassed. They're like, we spent 6 months collecting this data. We don't, half an hour doesn't really bother us. Anyway, so that's some benchmarks for there. I won't give you, there are lots of empirical results of my own system available on the web page, so you can look it up there if you so wish. All those results are using Cplex, so we use the skip system, but the skip system has the option of using Cplex to solve the linear relaxations. If you don't use Cplex but use skip's own system, everything will be a lot slower. So link it to Cplex if you want the performance, if you have Cplex. Or Ruby. So that's, I won't say anything more about that. Here's another thing. So most of the results you've seen so far are where you said, right, we've got this so-called optimal Bayesian network learning thing, but by the way, we're going to limit the number of parents that any node can have. So that's kind of cheating. What you really want to know is, I've got this data set, I want to find the optimal network without any restrictions. Yeah? Just find it for me. I don't need stuff. So our own system, how well does this work? So I grabbed some data sets that originally came from the UCI and put low parent set restrictions. So for example, these guys here, you can have 22 parents. Yeah? How does it do? So this is a number of variables. This is a number of data points in the data set. This is a number of IP variables once you've created them. This is how long it takes to find the local scores for each one of those variables. And this is how long it takes to solve for IP once you've constructed it. Okay? So these two numbers added together is how long the whole thing takes. So there's some interesting things here. So one thing is that it's the number of variables that matters. So this guy here, we've got 30,000 data points, but we've only got 14 variables. So it only takes 4 seconds to compute all these scores, and 11 seconds to solve the thing. All right? So because there aren't many variables. Down here, let's have a look here. Yeah, 23 variables, a few more, only 8,000 data points. We run out of time even before we construct the IP. We fail at that point. So it's the number of variables, not the size of the data, that's the real killer here. Yeah. So sometimes it works, sometimes it doesn't. You've got the situations where it takes thousands of, more than 1,000 seconds to compute these local scores. Once you've got them, you solve it in less than a second. So, so also we get a fair number of failures. So this just gives you a kind of rough idea of what you can expect, at least from my system. These slides are on my homepage, by the way. Okay, and other data sets, full disclosure as they say, other data sets which I downloaded, they all failed on. So all these ones, which are bigger than the ones I showed in the table, with more variables, it failed on all of them. But what I should mention, by the way, that for example, this guy here, it failed, it ran out of time. I think I had a 2-hour time limit, I can't quite remember now. But at that point, we had a Bayesian network which we knew was in 0.88% of the optimal one. Because we've always got these bounds. You know, we've got the best network we've found so far, and we've got some global upper bounds, so we can look at the gap. So even though this one didn't prove that the one it had is optimal, it's either optimal or very close to optimal. So you have these anytime things which are nice. Over here, the gap was a bit bigger. Okay, where are we? Yes, so I should mention Peter van Beek's work, which will be presented at the CD conference in Cork this summer. So he did a comparison between a constraint programming-based approach, my system, one old version of my system, and Changhe's system, a star. My new version is a bit better, but not massively so. And here are his results. So you'll see, well, there's a lot going on here. Basically, you'll see that in many cases, his system does very, very well. Here's a particularly bad case. Malone takes 5,000 seconds. This takes 1.4 seconds. There you go. Another case is where Malone takes 1.6 seconds and 6.9 seconds, and the other systems run out of time, and vice versa. So what you're getting here is that different approaches to Bayesian optimal Bayesian network learning have radically different performance on different items. So I think that's a good takeaway point. You know, There's no one best system at present, that's for sure. So how do they compare? I mean, if you've got a particular problem, which one to go for? Well, here's a useful graph. So here we have a bunch of problem instances where we've got the number of Bayesian network variables, not the number of integer programs. We have a number of Bayesian network variables, and these are the number of candidate parent sets, which in my case get encoded as IP variables. And these are different problem instances. The red dots are where Changhe's system solved it more quickly, and the blue ones are where my system solved it more quickly. So you'll see they're very different. So with the ILP system, you can get away with having many variables in your Bayesian network as long as you don't have too many possible parent sets. Whereas the A-star thing does better in the other direction. The X's are where they both fail. So, that motivates using a portfolio approach. You say, here comes my problem. Oh, it's one of these problems. We'll send it to A-star. Oh, we'll send it to the ILP side. That's an obvious thing to do, and that has been done. So here's a paper from last year. So we have, this is a number of instances solved in a given time. So here we have another competing algorithm, didn't do so great. Here we have A-star. Okay, and here we have Goblin. All right, Goblin was doing slightly better. However, using very simple ways of choosing between blue and red here, we can end up with this portfolio approach, which is the one to go for, clearly. And interestingly enough, this is very close to this virtual best solution where you sort of cheat and choose the right one after the event. So it's quite easy to choose which, at least between these two algorithms, which is the one to go for, and you can kind of do a portfolio solver. So that's kind of interesting. So another thing, to return again to this optimal learning, so we've got these solvers which, if they solve the problem, will give you a guaranteed optimal solution. Is it really worth the effort? Maybe it'd be better to use some heuristic solution, which maybe will crash less often, won't run out of memory so readily, and maybe won't give me the optimal, or at least guaranteed optimal high-scoring Bayesian network, but maybe we don't care so much about that. Is there any benefit to it? Well, there's a paper to be presented at this conference by Brandon. Our speaker hasn't turned up yet, so I won't say too much about it, but the take-home points are that two things. One, if you're trying to learn a Bayesian network, you should give it as much data as possible. No big surprise there. You'll end up with one closer to the true network if you have more data available. I think anyone will be surprised by that. And also, the optimal learning approach is generally finding a network with the highest score does generally give you a better generalization, which means the scores we choose are kind of reasonable ones. And the full results you can see elsewhere. But it is worth the effort, or one way of putting it is, you may as well run it, see if you get an optimal solution. If you do, that's good. If it fails, try a heuristic approach, because at least you'll get something there. Okay, and I'm pretty much done. So acknowledgements, as I mentioned, my system was developed for statistical genetic purposes, so we got funded by the Medical Research Council, funding is now sadly over. And this visit was funded by the UK National Centre for the Replacement, Refinement and Reduction of Animals in Research. It's a different project now. And thanks to Peter for discussions about his CP data approach. And there are papers and things. Yeah. Okay, we've got 5 minutes for questions.
On the pedigree data, you were showing percent correct, essentially.
Yeah.
How was ground truth? How was ground truth in that data set obtained? How did you know what to?
Because we had the ground truth is this. That's the ground truth.
Right.
We generated synthetic data from that ground truth. Yeah.
Got it. So you're assuming that this is true.
Well,
yes.
we don't really care. If it's
You're
true.
generating from this. I see.
All we know is the data came from here.
Got it. Got it. Okay.
Yeah, people have told us that this actually happened, but I'm 100% convinced they've got every single marriage connection. Right. It seems a little bit. The data came from here, so in a sense it doesn't matter.
I see. Got it.
And there was another question.
Yeah, but the same data set, because you know there are only 2 parents, do you need any other constraints to reduce complexity?
You don't need, well, you should have other constraints. So one thing you've got to be careful about is that suppose the individuals in here, you don't know their sex. All right? It has to be the case but you must be able to consistently assign sex to every node in the thing. So 2 men cannot have a baby, 2 women cannot have a baby. So then you have to add, to do it properly, which we have done, you have to have extra variables which encode the sex of each individual. And there has been extra constraint saying that these sexes can be consistently assigned. Of course, in some cases you may know the sexes, in which case you just fix these variables wherever they are. So the only other constraint is sex consistency. So I skipped over. I mean, you can add other constraints if you're doing a real pedigree or anything. You do things like you say, basically, the gap between the age. If you have ages, things will go a lot easier. So if you know the ages of your individuals, then obviously you can't be older than your parents. So that makes the problem much easier. Obviously, we didn't put that in because otherwise there'd be no challenge. We pretended we didn't know the ages of all these people.
No more questions? Okay, Changhe and James, thank you very much for this very nice tutorial. Thanks for being on time. Enjoy your coffee and we'll meet again at 10:40.